Welcome everyone. We are here to explore fraud classification using credit card transaction data from Kaggle. And the best part is our entire study will be conducted in Google Colab using Python programming. By the end of this video, you will be able to use Keras sequential model, logistic regression, as well as how to resolve class imbalance by applying synthetic minority oversampling technique. We will also evaluate and improvise the model performance step by step. So keep watching. In general, a binary data classification pipeline for credit card analysis involves few key steps, like loading the data. I think that's important for any kind of analysis, right? So let's go through that. So first will be data preparation. To gather and pre-process credit card transaction data, addressing different missing values, outliers, and potential data quality issues. Then we will do a data splitting to divide the data set in training and testing sets to train and evaluate the model's performance. Then comes feature engineering to extract and pre-process relevant features, including standardization or normalization of numerical features and encoding categorical features. Then comes handling class imbalance. To address class imbalance, we can employ different techniques like oversampling or undersampling. Then model selection. Model selection is to choose an appropriate binary classification algorithm, for example, logistic regression or decision tree or random forest, SVM or neural networks. Model training involves to train the selected model on the training dataset, tuning the hyperparameters for optimal performance. Then comes the crucial part, that's model evaluation. It is about the model's performance on the test dataset using metrics like accuracy, precision, recall, F1 score, ROC curve, and AUC. Model interpretation involves to understand feature importance and interpret model results for insights into fraudulent transaction detection. This entire pipeline aims to effectively detect fraudulent credit card transactions while minimizing false positives and ensuring that the security and stability of the system. As per the discussion, let's start with loading our data. I provided this Kaggle data link in the description. Sign in and download it. To begin with Colab, you can sign in to Google Colab and then ensure that you have been assigned to a free Colab account and mount the drive if you loaded the Kaggle data on it. Make sure to provide the right path for the CSV file, otherwise it's very hard to read the data. Now some of the imports like I have shown earlier, like import pandas, matplot library for data analysis and visualization purpose. So to start with, what we can do, we can store the data in a data frame called DF. The dataset contains all the credit card transaction details and the final class where 0 is non-fraudulent and 1 is fraudulent. Let me show you the data. The df.head, that shows the 3 rows in our data. And as you can see, the class where 0 is non-fraudulent and 1 is fraudulent. Now let's describe the data. The describe method returns a description of data frame's data. If the data frame contains any numerical data, the description includes the following details for each column, like count, the number of values that are non-empty, then the mean, the average mean value, then the standard deviation, and the minimum, maximum, and all the percentile. Now is the time to check the distribution of the target class. In this code, df class.value counts, it calculates the count of each value, each unique value, I would say, in the class column from this data frame df. In the context of credit card fraud detection, it counts the occurrences of fraudulent and non-fraudulent transaction. And as you already know, plot.bar, it obtains the value counts using this previous method And this method is used to create a bar plot using the counts. The plot function is typically associated with the pandas library and the dot bar that specifies that we want to create a bar chart. The result is a bar chart representation, the distribution of fraudulent and non-fraudulent credit card transactions. The x-axis over here, that typically shows the categories like the fraudulent. The y-axis shows the count of transactions, and the bars of different heights, like you see here, 0 and 1. The heights represent the frequency of each category. The visualization helps in understanding the class distribution, which is essential for tasks like credit card fraud detection because it is an imbalanced data set with significantly more number of non-fraudulent transactions. That requires handling techniques, right? Now, from this graph, we can see the data set is an example of severe class imbalance, as shown in the bar plot, right? Wait, let me tell you about the class imbalance. It is a common issue in binary classification problems, where one class is significantly more in number from the other class. This issue can lead to biased and inaccurate model. If I create any model over here, I will get definitely more than 95% of accuracy, but that will be wrong, right? Now, the next step is to check if there is any null values in our feature. Now, df.isna function dot sound. So that provides the total number of missing values here. Luckily, we don't have any. Before any further analysis, let's find out total number of real transactions. So this code over here segregates the data set into two subsets. One for fraudulent transaction as fraud and the other for real transactions as real. It then calculates and prints the numbers and percentage of transaction in each category. It providing the insights into the class distribution of our data. As we see here, our total number of real transaction is like 99.8%, right? Similarly, no fraud transactions, that could be around 492. And the percentage of fraud transaction is 0.173%, right? This code generates a heat map to visualize the correlation between different features in our data frame DF. It calculates the correlation matrix and uses SHE1 library to create the heat map. The heat map displays the strength and direction of the relationships between features with annotated values of each correlation. It is a useful tool, I must say, for identifying different patterns and different dependencies in our data, especially in tasks like feature selection and understanding how variables interact with each other. The plot.title function adds a title to the heat map plot. As we can see here, there is no severe correlation. So we can keep all the features so far. Let's see what it happens. Next feature is distribution of transaction amount. From this plot, we can say that most of our transactions are between 0 to 3,000. Let's check the distribution of fraud transaction and real transactions. According to this chart, the majority of fraudulent transactions involve amounts of less than $550. This also demonstrates that there is a high probability of fraud for a transaction amount which are close to 0. So let's determine what is the maximum amount of fraud transaction. So it is $2,125.87, and the minimum is obviously 0. So let's get to the time distribution. We need to figure it out what time this transaction happens, right? So plot.figure, this sets the figure size for the plot to the units, like whatever unit you mentioned, like 6x4 I have mentioned. Then the title provides the distribution of transaction with respect to time, and we can also set the font size here. Now, sns.distplot of df time, this is a common uses of C1 library to create distribution plot or histogram, we can say, for the time feature from the data frame DF. It specifies the number of beans for the histogram we'll use, like 120 I have mentioned here. That generally determines the granularity for the distribution visualization. And as you already know, plot.show finally the command to display the plot. When we look at this graph, we can see that there are two peaks over here, two high peaks, and even one small peak, right? So we can think of this as a time of the day. For example, the peak is when most of our activities happen, which is during the day. And the depth of is most people are sleeping, right? We already know that the data only has credit card transaction for 2 days. So there are two peaks for daytime and one depth for nighttime. In this shell, I created a single function to generate all the above analysis in a single click. After exploring the data features, it's time to standardize our data. Standardization and normalization are required before model building to ensure that features are on a similar scale. It prevents certain algorithms from converging slowly and make the models more interpretable. The code defines a function called scale normalize and log transform column, right? That takes a data frame DF and a column name as input. It then performs 3 data transformation on the specific column. Standardization, it scales the value in the column to have a mean of 0 and standard deviation as 1. Now normalization, it basically scales the values in the column to the range between again 0 to 1. As we already got our normalized data, now we can split the data. For this code, the test size parameter specifies that 30% of our data will be used for testing, and the random state parameter makes sure to reuse by fixing the random state. The shuffle equal to true parameter shuffles the data before splitting it. I would say it is a good practice to avoid any order-related biases in our data. Now comes the baseline model. So what is a baseline model? A baseline model is required to provide a simple benchmark performance level for comparison when developing more complex models. It serves as a reference point to assess whether advanced models are making meaningful improvement in predictive accuracy or other performance metrics. So we can start with a simple logistic regression. The code over here trains a logistic regression model on imbalanced data and evaluates its performance using classification metrics. It fits a logistic regression model to the training data and then makes the prediction on the test data. Next, it prints the classification report over here that includes different matrices like precision, recall, F1 score to assess the model's performance. To better understanding, I created another function called print classification metrics, where we got accuracy around 99% here. Well, that's a lot. To get a better understanding, I created another function called print classification metrics, where we got accuracy as 99%, then AUC as 0.81, precision as 0.65, recall as 0.63, F1 as 0.64. Oh my God. Let's take a pause here and cross-check the result we got. If there is any confusion, let's clarify by using a confusion matrix. So confusion matrix takes Y test and Y prediction to provide a matrix over here. The true negative is like 85,251 number, that is genuine transactions correctly identified as real. Then true positive is like 92, the fraudulent transactions correctly identified as fraud. Then the false negative, that shows fraudulent transactions incorrectly identified as genuine. Then the false positive, like 48 instances. That is genuine transactions incorrectly identified as fraud. Here comes another evaluation metric, ROC curve. It identifies how well classification problems work at different levels. It is basically a probability curve, and the better model is predicting whether a transaction is fraud or not. The higher the area under the curve number, the better is the performance. It is a way to measure how well the model can tell the difference between two possible results. It shows if a model can clarify or clearly divide the positive class from the negative class. Now here the matrix, this function takes two input y test as true class levels and y prediction as predicted class levels for the probability score for the test data. Let me see what's the score. It's 81.91. We can still make it better. Here is the time to plot our ROC curve. The function plot ROC curve generates and displays a receiver operating characteristics curve for evaluating the performance of binary classification model. The function takes two arguments, like as you see, y test and y prediction. Y test as our true class levels, y prediction as the predicted class levels or the probability scores for the test data. Then it creates a figure with a specified size we can mention, like 6 unit wide by 5 unit tall. Now the ROC curve is calculated using a matrix.ROC curve function that computes the false positive rate and the true positive rate and the thresholds for different probability cutoffs. The area under curve is a score computed using matrix.ROC AUC score. It finds the ability to distinguish between positive and negative classes. The ROC curve is plotted using, again, plt.plot with the FPR, false positive rate, on the x-axis and true positive rate on the y-axis. To print a diagonal dashed line, I just mentioned y equal to x, that is added to the plot to represent random guessing, like helping to visualize how well the model performance is compared from the random channels. Now we got AUC score as 81.91%. As it is a class imbalance, so this result can be trusted. Now let's solve it by using synthetic minority oversampling method. Let's solve it by using synthetic minority oversampling method. In this method, we synthesize new data from the minority class rather than merely replicating existing data. Now let's recreate our logistic regression using SMOTE. Let's implement SMOTE right now and find out the original data shape and the resample data set. We need to make sure that both the classes are in equal size, right? There it goes. Now the class imbalance is gone. Now let's create logistic regression using our SMOTE sampling data. Now the code is performing logistic regression on our data set that has been balanced using synthetic minority oversampling technique. And it also evaluates the model's performance. Now let's break down the code here. The logistic regression max iter 1000. It basically initializes a logistic regression model with a specified maximum number of iterations. Now the logistic regression model is fitted to our balanced training data. Y prediction SMOTE, basically after training the model, is used to make sure the prediction using our Y prediction on the test data X test. Now print classification metrics. The function we created to print various classification metrics like accuracy, precision, recall, F1 score for evaluating our model's performance on our test data. The goal is to assess how well the model performs after addressing the class imbalance issue. The result of the model evaluations will be printed right now. So let's see. Wow, we got an accuracy as 98.2%. Our AUC is improved 93.2. Now let's see using a confusion matrix. So we got true negative as 83,852, true positive as 127, false negative as 17, and false positive as 1,447. That is the genuine transactions incorrectly identified as fraud. We significantly decreased the false positive from 52 to 17 by balancing out class. But still there is an issue in our false positive as it is increased to like 1,447 from 48. Well, that's the issue we need to address. So let's build a neural network. Like any model, we need to split the data set into train and test, then standardize the features. Now for building the neural network, we need some of the parameters like tf.keras sequential. This basically creates a sequential neural network model while layers will be stacked sequentially. Now tf.layers dense 128 with the activation as ReLU, input shape as xtrain.shape1. Basically, this is a first layer to our dense layer or fully connected layer with 128 units and ReLU activation function. It specifies the input shape based on the number of features in the training data by using xtrain.shape1. Now tf.keras layer dropout as 0.2. A dropout layer is added with a dropout rate of 0.2. It is basically a regularization technique that helps to prevent overfitting by randomly deactivating the some fraction of the neurons during the training, like 0.2 fraction. Now tf.keras layers dense 64 with activation ReLU. It is another dense layer with 64 units of ReLU activation function. Now again, we can add a dropout layer. It is basically to provide the regularization technique as I mentioned earlier. Now tf.keras layer dense as 1 with the activation sigmoid. This is our final dense layer with a single unit and sigmoid activation function is added, which is typically for binary classification tasks. Now is the time to compile our model. Model.compile, this is basically the step compiles the model, specifying the optimizer as Adam. In this case, the loss function is binary cross entropy for basically binary classification problem. And the metric is to monitor during our training, that is accuracy is what we are going to measure, right? Now the model training. Model.fit is basically the model is trained in our training data xtrain and ytrain for 10 number of epochs with a batch size of 128. Now the validation split of 20% is used for monitoring validation performance during our training. Now model evaluation. This is an important part. So loss and accuracy. This is what we're going to evaluate by using model.evaluate xtrain and ytest. After training the model's performance, it is evaluated using test data like xtest and ytest. The code basically computes both the loss and accuracy on the test data. Lastly, you can print our result, like the test loss and the accuracy are basically printed to assess how well the trained model performs in our unseen data. Now you can start this training. It might take some time. There we go. Not bad, not bad. Few more seconds to go, 5 more. I think this is the fast one I'm seeing. The last one. As we already trained, let's make our prediction and print out confusion matrix and classification report. True negative as 56,855, that is the genuine transactions correctly identified as real. Then true positive, that is 74, fraudulent transactions correctly identified as fraud. Now false negative is 24, that is fraudulent transactions incorrectly identified as genuine. Now false positive, that is 9, genuine transactions incorrectly identified as fraud. I'd say it is a better result with lower false positives from 1447 to 9. I guess that's the power of neural network. There is still some other methods like LSTM to improve the model performance. We can use that later.
I hope you found this video interesting. Make sure to try out the code and drop your questions or any issues in the comment section. See you in the next video. Take care.